Hi, this is John Pace. I'm with the Computer Science Department, and I've been doing research on drone batteries, specifically seeing if it's possible to estimate the altitude of a drone by only looking at information taken from its battery during flight. Now, the motivation for this comes from the usage of drones in establishing temporary mobile networks. These are networks usually meant for disaster relief or military type applications. And when you create these networks, you need the drones to be in specific locations, but given the scenario, you may not have access to GPS or other traditional location services to tell you where each drone in the network is. So our goal is to see if we can use that battery information as a new method of predicting the drone's location. To do this, we used a DJI Mavic Air, that's just a normal portable consumer drone, and then I built a microcontroller that attaches to the battery of the drone, and it bridges the connection between the battery and the drone body. That microcontroller then measures the current and voltage from the battery. It logs that information, and then it transmits it back to a program I have running on a laptop to do live predictions. This plot shows an example of what that data looks like. This is current draw taken from the battery of the drone during flight. Now, each different flight behavior of the drone has a unique current pattern to it, or a unique waveform. And it's these unique waveforms that we're trying to detect to determine what flight state that the drone is in. Now, to do that, I have a program that looks at the last 4 seconds worth of battery readings. And with that information, it finds all the peaks and all the craters within the waveform, their distances, their amplitudes, the averages, and then it uses that as a feature set to determine what flight state that the drone is in. So just for some quick examples of what these unique wave patterns kind of look like, this plot shows the current and voltage information of the drone while it's doing its automated takeoff sequence. Now this sequence is hard-coded into the drone software, so it doesn't change that much, but other flight patterns, that's not quite the case. So in this plot, the drone is going through 2 of basically the same flight maneuver. It's climbing up, coming back down, it's climbing up again, and then coming back down. And you can see the wave pattern for each of these maneuvers it's different. And it's these kind of varying unique wave patterns that my software is looking for to determine what flight state the drone is in. Once I have the flight state classified, if it's hovering, if it's ascending, descending, I then have a formula that does a mapping from the current to an acceleration value. And this is what my calculated acceleration using nothing but that battery information looks like compared to what an acceleration sensor on the drone itself thinks its acceleration is. Once I have this acceleration predicted, I then map that to a velocity and then a position. So that's how I do my altitude estimation. And this last plot, that's just a quick example of what my estimated altitude is versus what the GPS data thinks its altitude is. And finally, I have just a quick demonstration of this working in real time. So in this clip, I have that microcontroller taking the current and voltage readings from the battery. It's then transmitting that information to a program I wrote that's running on the laptop. So you can see the measured current and measured voltage on screen there. Using that information, I then calculate what the acceleration should be, and then from there I can make a prediction of the drone's altitude. So I know that's a lot of information. I hope this made sense, and thank you for your time.